Hello physicists and welcome. In this session we'll be looking at Newton's laws of motion for rotation. Let's get started. Hey, let's quickly review our variables for both the linear and the rotational world. For position, x and theta. For velocity, v and omega. For acceleration, a and alpha. Hey, so now let's take a look at over a period of time. That'll be the same in both worlds, but our force in the linear world is our net force. Okay? And we'll be looking at mass as in kilograms. In the rotational world, we still use the value T. The rotational analogy for force is torque. And the rotational analogy for mass is the moment of inertia, or the difficulty in getting something to rotate. Hey, let's take a look at our, calculations between the two. Our position, velocity, and acceleration values are really just the rotational value times the radius. Hey, let's take a look at our force. Okay, our radius at which the force is applied times the force is our torque, and our mass, or our moment of inertia, is equal to the integral of r squared dm. For a point mass, that's pretty straightforward. It's just the mass m times the radius squared. Hey, so what causes torque? And what I'm defining as a torque is a force that's capable of causing angular acceleration. Hey, first is that forces are not acting along the same line of force. Let's go take a quick look at that. If I have a box here, and on one side I'm applying a force like that, and the other side I'm applying a force here. Our two forces are not acting along the same line. Okay, that's one way we can cause a torque or a rotating force. Hey, the other is that we have a force not acting through the center of mass. Again, let me take a box here, and I'll mark the center of mass right here. Hey, now up until now, we've always assumed that our force is applied through the center of mass, so there's no rotation. Now we're going to start looking at, hey, what if I were to apply my force here? That line of force does not pass through the center of mass. Those are our two conditions where we'll have a torque or a force that's capable of causing an angular acceleration. Let's take a look at Newton's three laws. So Newton's laws for rotation. The first law, an object at rest will remain at rest, and an object spinning will remain spinning about the same axis and at the same rotational speed unless acted on by an unbalanced torque. Sounds pretty familiar compared to what we've been looking at Newton's first law. An object at rest remains at rest, and an object in motion remains in motion unless acted on by an unbalanced force. Well, this one we just substitute the word spinning and torque for motion and force. And so just a note, we can read Newton's laws forward and backwards. So in other words, if our angular velocity is constant, then our net torque must be equal to 0. Hey, let's take a look at Newton's second law. Okay, an object will change its angular velocity, or another way of saying it's our rotational speed, in proportion to the unbalanced torque and inversely to the moment of inertia, what I'm calling sometimes rotational mass or rotational inertia. Hey, so we have the calculations or our equations here, and they look very familiar compared to Newton's second law. In Newton's second law in the linear world, we end up saying that, hey, acceleration is proportional to the net force divided by mass. Here we have angular acceleration is equal to the net torque when we add up all of our torques, whatever we have left over, divided by the moment of inertia. Or we'll put it in its more famous cousin's format, that F equals ma. We could say torque is equal to moment of inertia times the angular acceleration. Hey, so in other words, if the angular velocity changes, then the net torque is not equal to 0. Hey, so let's take a look at Newton's third law for rotation. And there's going to be an important note here. Newton's third law, for every force, object A on B, there's an equal and opposite force, object B on A, equal in type, equal in magnitude, and opposite in direction. Yes, I bolded and underlined the word force, because in this case, we would not say for every torque there is an equal and opposite torque. That is not actually correct. So I have this note here. So notice it says force, not torque. This is really important for gears and levers because we want to end up multiplying, if you want to call it that, the force depending on how long our moment arm or our lever is. Let's take a look at the moment of inertia, what I also call the rotational inertia or rotational mass. And so as we've seen in class that both the mass and its distribution from the axis of rotation change the rotational inertia of an object or its difficulty in getting it started and stopped. We calculate that by looking at the moment of inertia is the integral of our distributed mass times its distance squared from the axis of rotation, given in this equation here. Hey, in the simple case, if all of our mass is at one point, there's no distribution, we end up just having the value of mass times radius squared. Right. Hey, and so a note, if we have a distributed mass, then our dm needs to be expressed in terms of mass with respect to r. Hey, so let's take a look at moment of inertia for some common shapes. In class, we've looked at the derivation of moment of inertia, but let's take a look at some common shapes. Hey, I have a point mass at a position r, so let's say I've got my blob over here. This would be my radius, and I have some mass out here. Okay, and I'll put it on a thin string or something like that. With that, no mass. Hey, the moment of inertia of this is mass times radius squared. Hey, let's have a slightly different thing. Our slender rod about an end, so we'll end up having a rod. It has mass m. It has length L. And let's say I were to rotate it about one end. The moment of inertia of that, if we add up all of these little pieces in here, we make them infinitely small and add them up, we find that the moment of inertia is equal to 1/3 our mass times our length squared. Now let's take a look at something related to this, and that's a slender rod length L about its center. So again, we'll have a slender rod here. Mass uniformly distributed, length L, but in this case, we're looking at rotating it about the center right here. And we do the integral, we find that the moment of inertia is 1/12 the mass of the rod times L squared. Hey, one other shape that's going to be important, and that is a disc, radius r about its center. So, best I can, I'll try drawing this. Okay, in this case, we have a radius here, and we'll assume that the density all the way across this disk, it has a certain thickness to it. We got a view of it there. All right, we have a uniform distribution of mass. The mass of that is 1/2 mass times radius squared. Perhaps you can see that it's a little bit more than our rod about the end, because as we go out, the amount of mass actually gets greater and greater at any position r, because we end up having the whole annular region, which gets larger and larger as we move from the center of axis of rotation. Hey, so let's look at some sample problems here. Hey, so we have a duck, mass 2.4 kilogram, stands on a weightless beam 2 meters from the left end, and the beam is at rest and is 3 meters long, supported at each end. Calculate the torque about the left support, caused by 1, the duck, and 2, the right support. Hey, when doing these rotational problems, what's nice is we can pick the axis of rotation. We'll tend to pick something that ends up being, let's see, pretty convenient. This spot over on the left side, well, one, we're given it, but the other one is any force that's acting through this spot on the left side has no radius, so it produces no torque. Let's go ahead and answer this. Okay. Hey, so A, let's see, we want to know the torque about the left support. Now we know that torque is R cross product F. Hey, this has its full value when R, the radius from R rotation, and F are at right angles. So we can look at this as also being r times F times the sine of the angle between those two vectors. I'm going to call that radius a vector and that force a vector. You can see our duck is going to produce force of gravity on the, let's see, for the duck. You can see that that's at right angles compared to this vector r. Okay, let's go ahead and figure that out. Okay, so sine of 90 degrees is 1. So let's go our radius here. 2 meters, the force on the duck, 2.4 kilograms times our 10 newtons per kilograms times. So the weight of our duck is 24 newtons. Hey, the torque due to the duck here is 48 Newton meters. Let me go ahead and put a box around that. Hey, something to note. See, it says Newton meters here. We can't call that joules. Why is that? Because it's a cross product. We have our newtons going down and our meters going to the right to cause a twisting force. Okay, our force is not in the direction of our distance here. If the newtons and the meters were in the same direction as we were doing with energy, then a Newton meter becomes a joule. But in this case, it is a Newton meter, a measure of torque. All right. Hey, so we've got the torque due to the duck. The second part, B, is asking for, hey, so what is the torque about the left support caused by the right support? Hey, so our duck is causing I'll call this a clockwise torque. Our beam is still, so we know the net torques are equal to 0. So our beam on this side must be causing a counterclockwise torque, and it has to balance this. So even without doing much in the way of calculation, I can see that it has to be 48 Newton meters counterclockwise. All right. Let's take a look at another sample problem. Got 4 of them here. This is our first. And, whoa, let's see. Forgot to put the floor in there. All right. Hey, so let's take a look at our second problem. We have a uniform beam, 4 meters, has a mass of 7 kilograms, is pinned to a building, free to rotate. So we have a pin right here. It can rotate pretty easily. A 9 kilogram box rests on the beam 1.5 meters from the pivot. A cable runs from 3 meters above the pivot to the end of the beam. Calculate the tension in the cable. All right, let's go ahead and do that. Hey, so again, I'm free to pick whatever point I want to for doing my rotation, and it looks like this spot right here, right where the beam hits the wall, will be a good place to do that because, one, I know it rotates freely, and also any forces here will not produce any torque. So I know there's probably going to be a force upward supporting it, maybe even a force from the left, but neither of those will produce torque, so it makes life easier. All right. Hey, also, this is at rest. Yep, it rests. Okay, so we know that the sum of our torques is equal to 0. Let's go ahead and get started. Hey, so we're going to take a look at the torque due to the beam. We'll take a look at the torque due to the box. Both those appear that they're going to produce a clockwise torque, and then we're going to have some type of a force that's going to spin it back the other way. So we're going to have the torque from the cable will be counterclockwise. And let's take a look at the torque from the beam. Hey, when we have it uniformly distributed, we can think of it as all of the forces acting at the midpoint of our beam. Okay, we're going to have a force of gravity down from that 2 meters from our pivot point. Okay, so the torque from the beam, R cross F, that distance, 2 meters. These are at 90 degrees, so I can get the full value of my torque here. The distance, it's a 4-meter beam. Oops, okay, so our distance is 2 meters. The mass of it is 7 kilograms, so the gravitational force is 70 newtons. Hey, so I'm producing 140 Newton meters of torque about this point on the wall, okay, from the beam. Let's take a look at the box. Again, R cross F. Our box is 1.5 meters. That's straight down. Again, that's 90 degrees from our radius out from the wall, so we can use that full value there. Okay, that's 90 newtons, 9 kilograms times 10 newtons per kilograms. And I get, let's see if I do that right, what do I get? 135 Newton meters. Okay, so our total torque clockwise is what? 275 Newton meters. Hey, and that has to be balanced by the torque provided by the cable. Hey, so our torque from the cable is going to have to be what? R cross F. And the force will be that tension in the cable. Hey, notice this time that our cross product or our angle here is not 90 degrees. So we're going to have to look at the sign between the two. Hey, this happens to be, it's 3 meters here, and we find that this is 4 meters. So 3 squared, 4 squared, add them together, I get 25 divided, take the square root of that. I see that this is 5 meters long. All right, that's going to come in handy because now I can say, hey, 275 is equal to, what's the radius here? 4 meters times the force in the cable times the sine of this angle. I'll call that theta. And the sine of that angle is equal to 3 divided by 5.6. Let's go into a little bit of math here. So our force in the cable is going to be equal to 275 Newton meters divided by 4 meters times 0.6. What do I do? I put that in the calculator. I get what? 114.6 newtons is the tension in that cable. Now you can probably see that it would be more effective if I had my cable pointing straight up. I wouldn't have as much tension in it. As I get lower and lower, the tension in that cable will become more and more because the upward component still has to be whatever that has to be, around what? 60, I guess around 68 newtons has to be the vertical component of whatever we have. So if I get a shallower and shallower angle, the vertical component still has to be 68 newtons to create this amount of torque. 275 divided by 4 meters, right? And so 114.6, hopefully that cable is strong enough to hold that up. All right, let's take a look at another example here. Hey, you got a disc, a mass 4 kilograms, diameter 6 meters, has rocket thrusters. There's one rocket thruster, another rocket thruster along the outer edge. The rocket thrusters apply a force of 15 newtons each. A, calculate the angular acceleration of the disc, and B, determine the time required to reach a rotational rate of 10 revolutions per second. Hey, so notice that this is saying revolutions per second, not radians per second, so we'll have to be a little bit careful there. Hey, and assume the mass of the rocket thrusters is negligible. Hey, so we're looking for angular acceleration. That works out well because our angular acceleration, as we know, is our net torque divided by our moment of inertia. It's analogous to A equals F net over M. All right. Hey, let's take a look at our net torque. And so what do we have? We have 2 of these rocket thrusters. 1, 2. Okay. Hey, and what's nice is they're located, where was this thing drawing? Hey, there we go. Hey, they're each located 0.3 meters from the center of that disc. Hey, so our torque is going to be 2 because we get 2 rocket thrusters. R cross F. Hey, our radius and the direction that the force is being applied are at 90 degrees, so we can just go ahead and multiply that thing. So we end up saying, hey, it's 2 times 0.3 meters times 15 newtons. What do I get? I get 9 Newton meters of torque. Hey, what's our moment of inertia? We saw from some of our simple arrangements that it's equal to 1/2 mass radius squared for a disk. So that's going to be 1/2 mass of the disk, 4 kilograms. Our radius squared, 0.3 meters squared. I multiply all that out, and I get, what's the value? 0.18 kilogram meters squared. Hey, so my alpha is equal to 9 Newton meters divided by 0.18 kilogram meters squared. If I look at all the units, remember a Newton is a kilogram meter per second squared. Kilograms cancel. We'll have meters squared on the top, meters squared on the bottom. We have this interesting thing where our units at the end are acceleration 50 nothings, okay, which is actually a radian per second squared. Okay, that's our angular acceleration. Hey, the next question is how long, right? Determine the time required to reach a rotational rate of 10 revolutions per second. I know that my final rotation rate is equal to my initial rotation rate plus alpha times time. It started from rest, so we know that's at a 0. My final rotational rate is 10 revolutions per second, but there's 2 pi of these radians in each one. So what do I end up with? I got 20 pi is equal to, let's see, 50 radians per second squared times t tells me that t is equal to 20 divided by 50 is 0.4 pi seconds. Let's go ahead and we'll put that into real numbers. And I get, let's see, 0.4 times pi, I get about what? 1.256 seconds. Make that decimal place a little bit bigger. Yeah, so what, 1.25 seconds to speed up once we put our rocket thrusters on there. All right. Hey, last example here. In this one, we have a 3 kilogram stick, 2.5 meters long, sits on the proverbial frozen lake. Yes, it is frictionless. All right. The stick is pushed with a horizontal force, not acting through the center of mass, with a force of 10 newtons, 0.6 meters from the center of mass. There's our center of mass. Calculate the angular acceleration of the board as it is pushed. Okay, so we're looking at angular acceleration. We could figure out pretty easily what the linear acceleration is. We just have our 10 meters divided by 3 kilograms, when we get 3.3 meters per second squared would be the center of mass rotation. Now we're going to look at the angular rotation. Hey, so we know that. Let's come back here. Angular acceleration is equal to our net torque divided by our moment of inertia. Hey, this one we only have one force, and we're going to pick our rotation. This is sitting on a frozen lake. It's going to tend to spin around its center of mass. Hey, so our torque in this case, there's only one force on it, is going to be R cross F. Okay, and this is pretty much a 90-degree angle here. Our R value running up this way, and our force to the right. You can see that those are at right angles, so we can use the full value here. We don't have to worry about that sine value. Okay, so our radius from the center, 0.6 meters. Our force, 10 newtons. Go ahead and multiply those. I get 6 Newton meters. Remember, don't call it oops, sorry about that. Don't call it a joule. How about I? Hey, we're rotating about the center of this, so we can use our standard formula, 1/12 ml squared. Let's go put some values in there. 1/12. Let's see, our mass in this case, 3 kilograms. Our length, 2.5 meters. Let's go ahead and square that. Let's see what we get. Put that in my calculator. I get, what do I get? 1.5625 kilogram meters squared. Hey, what's our alpha value, or the rate that we're accelerating? As long as we keep this force applied, we're going to have 6 Newton meters divided by 1.5625 kilogram meters squared. Found out before, remember, a Newton is a kilogram meter per second squared. Our meters there will cancel with that. One of the kilograms here will cancel, and we're left with just the value, the numeric value, 3.8, about 3.84. Our unitless value, radians, and we're left just with seconds squared on the bottom. Okay. Hey, an example here, if we end up having a force applied and there's no pivot. All right, so for now, that's physics.